Welcome all to Science for Alaska. If you're watching this live, good evening from Fairbanks. If you're watching this recorded, hello. Thank you for tuning in. My name is Carl Tape. I'll be giving this talk with Don Hampton. We're from University Alaska Fairbanks. Our talk is entitled Recording Alaska Auroras with Cameras, Magnetometers, and Seismometers. I'll start with an introduction and then 3 parts to the talk: historical background on aurora and magnetism, measuring the aurora, and then recording geomagnetic storms and auroras on seismometers. We're interested in auroras because they are beautiful, scientifically interesting, and in rare cases can pose a hazard to society. I'll start here with a time-lapse movie made by Don of a night sky in Alaska taken from Poker Flat. What you see here is a time-lapse image of the night sky, and you see the coastline of Alaska mapped. It's one camera's view, projected it to 120 kilometers altitude, so you get an idea of how big the aurora is just seen from one camera. And we see these bands of geomagnetic latitude, and that these aurora bands kind of seem to parallel them. But there's a lot of interesting behavior that happens away from those bands, and those are the things that we are really interested in. And if you watch here, this time is showing it's 9 hours from UTC time, so we're getting towards sort of 9-10 p.m. And we'll see here as it approaches 7:50 down here, a big burst in the sky coming up here. And there you see this dynamic behavior, and that's the kind of things that we're interested to capture. So what can we learn about aurora dynamics and complexities from measurements that are on the ground? This shows one particular snapshot of really a burst in the sky. And as an aside, this snapshot captures a rocket launch, which is another way to measure the aurora. Our talk will be looking at instruments on the ground. Monitoring the magnetic field has been of national and international interest since the 1800s. At the right, this shows the current magnetic observatories operated by the U.S. Geological Survey. And for reference, CMO here in the center, that's College Magnetic Observatory. That is up in the woods north of campus here in Fairbanks. One example of this societal relevance came, this paper was published in 2018 about a geomagnetic storm on August 4th, 1972. And here in the abstract it says, there was an additional effect long buried in the Vietnam War archives that add credence to the severity of the storm impact. Nearly instantaneous, unintended detonation of dozens of sea mines off the coast of Vietnam. And you can find this report, this declassified report, shown here with a map offshore Vietnam. And within that report is a figure, very small font here, but on the x-axis we see time in 1972. And on the y-axis it says number of mines active, numbering in the thousands. Solar storm is associated with August 4th, 1972. And then there's this replacement of solar storm losses. So kind of a reminder of the unintended connection between technology and the natural world in this case, and really high stakes for what is involved with these geomagnetic storms. Part 1, 1716 to 1741, I'll be looking at the discovery of the connection between aurora and magnetism. Our characters here are Edmund Halley of Halley's Comet, George Graham, a London watchmaker, Anders Celsius of the temperature scale, and a scientist from Sweden named Olof Hjorter. The events of this story take place in the north, so to orient ourselves, Fairbanks, here we are. We've got some information from London, Uppsala, Stuttgart, here's the North Pole, and even something from Philadelphia. So that's to reference ourselves. Not surprisingly, in a talk on the aurora, the emphasis is on the north. Paper in 1967 about Aurora and the Enlightenment opens with, during the night of 6th March 1716, a spectacular display of the Aurora Borealis was seen throughout Europe, from Ireland to Italy, It can hardly be supposed that this was the first display of such magnitude in all history, but it certainly caught the attention of scientists more than any previous occurrence. It engaged people at a time when they were scientifically curious about this phenomenon, and that's where our story will start. In London, they called on Halley to address the audience, talk about what had just been seen. This is the title of the paper, published in 1716 of the same year. It's entitled, An Account of the Late Surprising Appearance of the Light Seen in the Air on the 6th of March last, with an attempt to explain the principal phenomena thereof. So in this article, in trying to explain what everyone had just seen, Halley wrote this. There's a lot of text here. I've recopied it on the right. Wherefore, laying aside all hopes of being able to explain these things by the ordinary vapors or exhalations of the earth or waters, we are forced to have recourse to other sorts of effluvia of a much more subtle nature, and which perhaps may seem more adapted to bring about those wonderful and surprisingly quick motions we have seen. Such are the magnetical effluvia, whose atoms freely permeate the pores of the most solid bodies, meeting with no obstacle from the interposition of glass or marble or even gold itself. This is what scientifically you might call shooting from the hip. Halley turned out to be right on the mark in terms of invoking the magnetic field to try to explain the aurora. And as we might say, a picture is worth 1,000 words. This picture of the Earth at left and these lines emanating outward from the poles and inward, this was the Earth as a magnetic dipole as depicted by Halley in 1716. A textbook picture. If we fast forward 300 years and look in Wikipedia, we see a picture of the Earth as a dipole that's not that different from the basic inference that Halley had long before he was equipped with the mathematical theories at his disposal to really truly understand this. So there's our story. Starts in 1716. 6 years later in London, there's a paper published on these observations by George Graham, watchmaker. And George Graham carefully, hourly, for months, weeks, months, measured how a magnetic needle would be deflected day and night. And he says, I am well assured these changes in the direction are owing to some other cause than the friction of the needle upon the pin, but what that cause is, I cannot say. In other words, I have no idea what's happening, but the variation has been generally greatest for the same day between the hours of 12 and 4 in the afternoon, and the least about 6 or 7 in the evening. So Graham identified the magnetic field he's seeing is changing, doesn't know why. Two things caught the attention of Swedish geophysicist Anders Celsius. First was the March 1716 aurora display, and the second was Graham's report on these daily magnetic variations. In 1733, Celsius published a report in Latin entitled 316 Observations of the Northern Lights from 1716 to 1732, part by himself, part by others in Sweden. Basically, a catalog of description of aurora displays in Sweden. And the first entry, March 6th, 1716, the display that Halley had described and triggered so much interest across Europe. This prompted Celsius to develop methods and measurements for thinking about the sky, astronomy, and the aurora. And Celsius, between 1735 and 1740, he acquires instruments, including the magnetic compass from George Graham in London. Just to take us back, this isn't, click on Amazon, order, something arrives the next day. We're talking about long trips across the continent, in the ocean, meeting with people. So life is short, but he managed to acquire these instruments, had a geophysical observatory at Uppsala, Sweden constructed, and in 1740 began making these measurements. The observatory is still there in Uppsala. The seminal observations were made in 1741 in Uppsala. Celsius and Olaf Hjorter, his assistant, The title of this paper is about the many changes in the magnetic needle that the deceased Professor Anders Celsius noted and that have been further observed and are now presented by Olaf Peter Hjorter. So we'll look at what these observations are. The table at the right shows a list of dates and angular deflections by magnetic compass that coincided with aurora displays seen to the south. When the aurora is seen to the south, it's generally a big display. We're familiar with that here in Fairbanks. You generally are looking north. The first time I noticed the northern lights in the south and also a large change of the magnetic needle was on March 1st, 1741 in the evening. And there it is, March 1st, March 26th. And through this time, they've seen this some 40 more times, especially on April 5th. Hjorter wrote that he lists in this table the events when the large changes in the needle coincide with the northern lights seen in the south. The first three events occurred on March 1st, March 26th, and April 5th. As it turns out, they all coincided with auroral activity beyond Uppsala, including even Philadelphia. And the third magnetic event was independently recorded in London by George Graham. So in March 1741, as this is getting going, Celsius writes a letter to Graham in London asking him to start making hourly measurements of the magnetic compass declination. He doesn't mention anything about auroras. Just make these measurements, please. He gets a letter back from Graham to Celsius. I won't go through the whole notes, but basically at the end, Graham says, being alone on this day, I mean Sunday, the 5th of April, when the greatest alteration happened, the observations upon the other days were made with the same care, but they're much less. Basically, Graham says, on the 5th, there was this large deviation, and he has meticulous data to back that up. So the magnetic signal, April 5th, 1741, was recorded in both London and Uppsala at the same time, showing that the signal was one of at least continental scale. Was the 1741 aurora in Uppsala also seen elsewhere? The paper by Hjorter did not say, but we can dig up more and answer that question. In 1748, a Swedish scientist, Per Kalm, visits Philadelphia, and from none other than Benjamin Franklin, he collects someone's observations from Philadelphia about aurora observations. And we'll see, this is again published in Swedish, but the translation from 1741 of these aurora observations from Philadelphia, there are two entries, one on March 26th and one on September 27th. And if we look at those two, these two happen to be among the 19 nights of 1741 in Uppsala, where they observed large aurora and magnetic deviation. So pretty confident that certainly on this March 26th, these two dates where Philadelphia had aurora happened to be among the 19 where this more higher latitude Uppsala saw the aurora. So a really cool connection between that while aurora is being viewed in Uppsala, someone in Philadelphia is seeing that same aurora. And you can look into these catalogs to see further about these particular dates. 1873, German catalog, someone combines all these observations, and we can dig in this catalog and see on these dates where the Uppsala 3 observations are visible. We can also find the Kalm observation from Philadelphia, as well as from Petersburg, Utrecht, Boston. The one little tip you have to track is that the dates are off by 11 days due to the calendar, Julian and Gregorian. But anyway, it's clear that these big displays with magnetic deviation, these displays were seen in other parts of the northern hemisphere. So the summary of part 1. In March of 1741, magnetic deviations were observed in Sweden to coincide with aurora displays. The magnetic deviations were also measured in London, and the aurora displays were visible across Europe and North America. In the next section, Don is going to take over and tell us about the aurora.
Good evening. Thanks for coming to Science for Alaska, and thank you, Carl, for that great introduction. My name is Don Hampton. I'm a research faculty member here at the Geophysical Institute. And I'm going to sort of jump ahead here a little bit and discuss sort of how does the aurora produce these magnetic perturbations? I think Carl established pretty well that people were seeing that was the case. And then also try to talk a little bit why that might be important for us. So Carl was interested in showing the cast of characters for his stuff, and our cast of characters for this section are going to be some 19th century physicists from both France and England. And then since then, there's been a cast of hundreds of people who've been doing this kind of work. It would be fun to go back and talk about all of them, but we just don't have time to do that. And I wanted to get get you a sense of why we can see these magnetic perturbations and what they really mean and why they're important to us. So just to cut to the chase, the correlation between auroral activity and magnetic perturbations is now really well established. So what you can see here is the upper left, I've got a fluxgate magnetometer, which is the magnetometer we use here at the GI for doing some of the highly sensitive magnetic studies. We've got several of those in the field, and they're running 24/7. And basically, at any time, they're measuring what's happening with the magnetic field. And so what you see on the right are plots of 3 different stations where those are running. One's up at Tulloch Lake, which is a UAF research site. One is at Poker Flat, which is the site just north of Fairbanks. And one is at Trapper Creek, which is down near Talkeetna. And you can see for this night, we've got about a 12-hour period there. You can see things were actually pretty active. We've got deviations in the magnetic field by quite a bit. Now, in these, we're not actually plotting the total magnetic field. We've subtracted off the Earth's average magnetic field at these sites, and now all we're looking at is just perturbations. And these perturbations are well correlated with the aurora, and you can see that by the bottom where we have what we call a keogram. Now, to make a keogram, what we have is an all-sky imager on the left, and you take a slice in the north-south direction at each image that comes through, and then you just sort of stack those up as a time series. And you can see that all-sky image on the left. We've got several arcs there, but mostly they run east-west. And so if you take that north-south slice, you can just sort of see where the aurora is happening, located or relative to the location where that camera is sitting. In this case, it happens to be at Poker Flat. And so you can see sometimes the aurora is off to the north, sometimes it's off to the south. But you can see that when the aurora is most active, we often get very large perturbations in the magnetic field. And this happens night after night. What's interesting is sometimes you see there's some perturbations, and sometimes you don't see a lot of auroral activity, and that's interesting as well. But I can assure you that if there was a night with basically no aurora in the sky, all those lines from those magnetic sensors would be flat lines. There would be nothing going on. So it's clear that the aurora is actually causing these perturbations somehow. So we've been using these ground magnetometers for many, many years, certainly since the early 1800s, as Carl pointed out. And the reason is they're pretty simple instruments to work with. They're no longer any moving parts. What I showed you there is it's just all electronics now. The early ones did actually have some moving parts. They had little magnets inside of a chamber, and they actually moved around, and you measured how much they moved around. But now you can just do it by doing some electronic trickery. And the nice thing is they work when it's cloudy, they work when the sun's up, they work all the time. So you don't have to worry about not being able to see the aurora. So they are a good way of sensing when the aurora is happening. And in fact, they are the way that we do some indices for how active an aurora or a solar storm was. If you go to the aurora forecast page, you can see down there, there's a thing they call the KP index. That's the planetary K index. And that's just sort of the magnitude of the deviation of, or the perturbations in those magnetic field sensors from several places around the globe. That, by the way, that scale is sort of like the Richter scale in seismic work, in that it's not just linear, it's actually sort of logarithmic. So a KP index of 5 is sort of more like 10 times more active than the KP of 4. So we've got several indices that we use, and we use the magnetometers to define those. Again, because the cameras are not always working, especially during the summertime or when it's cloudy, you don't get the information you need. So magnetometers have been around for a long time, and we still use them quite extensively. So we've got magnetic perturbations, but I guess the question you have to ask yourself is, how do you make a magnetic field? Well, the answer is pretty simple, and these guys back in 1820 showed us how to do that. You make a current. If you flow an electric current, you're going to get a magnetic field associated with that. So these guys, Jean-Baptiste Biot and Félix Savart, worked in France in the late 18th, early 19th century, even in the mid-19th century. In about 1820, they came up with what is now called the Biot-Savart law. I don't think they called it that. that basically says an electrical current produces a magnetic field. And we know that quite well, but you have to think back in the kind of instruments they had, it was hard to come up with those kind of insights. And two things to think about that. The strength of that magnetic field that's produced is proportional to the current that's flowing. So if you have a small current, you get a small field. If you double that current, you double the field. And it also falls off from the distance from the current source. So if you measure the magnetic field right next to, say, this wire here that we're showing, right there, if you're right next to that wire, you're going to have a very strong field, whereas if you go a couple of meters away, you might not even be able to measure that. Now, it's good to be skeptical about these things, and you can test this out yourself if you want to. What I'm showing here is not much different than what BO Savart had, although it's somewhat modernized because of the Industrial Revolution and things like that. But if you've got a nice compass for guiding yourself and guiding yourself in the woods or whatever, and you've got a nice D-cell battery and a little piece of wire, you can actually take a look at creating this magnetic field. So here I've got a picture of what I did. Is I took an old piece of wood I had, I don't need it, and I just drilled a couple of holes. I took a piece of Romex from like house wiring. It's nice and stiff copper, and then I took a D-cell battery, and so I made it so you could put the D-cell battery on one side and then touch the top part of the wire to the other side. And then right next to this wire going vertically, sort of like this wire over here, I put the compass. And I had the compass sort of pointing toward the wire at that point, because as you'll see in a second, it actually wants to go the other way. And then what I did, you can see right here, I just touched it there, and you can see now the compass needle, when I touch the battery and have a current flowing there, that compass needle deviates. Then I reverse the battery, so I have the current going the other way. And if you look carefully, this needle actually bends the other way. For some reason, it's a little slow there, but it does finally end up going back there. And then you let go of the current, you stop the current, it goes back to its normal state. So it's an easy thing to do at home. A couple of pieces of warning. I would use a D-cell just because that battery does get a little bit warm. And I would definitely not use a lithium-ion battery of any sort, because the reason you can do this is because that battery has a little bit of resistance inside. Lithium-ion battery doesn't, so you'd have a lot more current. It would get very hot very fast, and you don't want to. I don't want to see people's houses burn down because they're trying to do that. So use a D-cell alkaline battery. So that's how you make a magnetic field. You just flow a current, and honestly, that's pretty much all that's happening with the perturbations that we see of the aurora. It turns out there is a current flowing up in our upper atmosphere, and that current, in this case, I've got the current flowing into the board, so it's pointing away from us. North is to the right, and we're looking to the west. And if we've got that current flowing up there, it's going to be in this sort of circular pattern here. And then if you measure at 3 different places, like Tulik and Poker and Trapper, you can actually see slightly different orientations of that field because you've got these circular fields here. So that's how we know it's about 100 kilometers up, because this is somewhat localized, and when you have a string of sensors like this, you can do that. And also remember I said the further away you get, the smaller the field would get, and as you view that, as you move away from that center position, you can actually see the strength of the field, those perturbations go down. And by doing that, we can figure this current flow is about 100 to 200 kilometers altitude, 60 to 120 miles up. And it's typically associated where the aurora is. And you can see that, here's another example. We have a magnetic sensor chain here in Alaska, but a lot of other places do as well. And the Scandinavians have been measuring aurora for quite a bit. And they've got a string of magnetometers as well. And here is a time series plot of a whole bunch of those. And I've sort of associated each one of those. What they've got is stacked here by latitude. So these are the most northern ones, these are the most southern ones down here. And I've sort of associated them here across to a couple of the stations. And you can see up here on Svalbard, you've got quite a bit of perturbation at this time, whereas down here, I think that's Karstad, at the same time, there's very little perturbation in the magnetic field down there. So that means that this magnetic perturbations were associated with currents that were flowing up in this region here. All of these guys show very strong currents. And you can see other times as well, you can see strong perturbations here in sort of the middle latitude, but not stuff in the top. So you can see that region where that current flows and creates those magnetic perturbations moves in latitude as well. And certainly we've put together calculations to try to figure out where these currents are flowing by doing this. But that still doesn't answer why there are currents in the upper atmosphere. And so now let's try to talk a little bit about that. To create an electric current, you need two things. One, you need a source of energy, and then when you're trying to flow currents, that means some sort of voltage, which is an electrical potential. So what you need is a battery. You need a battery or a power supply or a dynamo or something like that. And then you need something to flow that current in. If you took a piece of just regular plastic and put a battery on the other side of it, you're not going to flow a current because that's not a conductor. It needs to conduct electricity. So typically what you need is a wire. In the example I showed at home, I just used a wire. Well, for the aurora, it turns out the battery really comes from the interaction of our sun's solar wind and the Earth's magnetosphere. The magnetosphere is this region. Here's a diagram here of the Earth down there, and magnetic field has these sort of symmetric bars that Carl showed earlier. When it gets into the solar wind, it actually gets blown back by the solar wind. I'll talk about that in a second. But this whole region where Earth's magnetic field dominates is what we call the magnetosphere. And because there's so much dynamics going on between the solar wind and that magnetosphere, there are lots of currents and things happening in that, and that creates that battery that we need. The wire is an atmospheric layer, an upper atmospheric layer that we call the ionosphere, and it's enhanced at times by ionization caused by the aurora, and that's what creates the wire. So we'll talk about those in a second. So let's talk about the solar wind. All of the energy that goes into what we call space weather or space dynamics or in the aurora, it's all caused by the solar wind. All comes from there. So the sun is hot. I mean, I think we can all agree with that. And if you think about putting a cup of tea on your kitchen table in the morning and the sun streaming through, that hot cup of tea actually has a bit of water vapor coming off the top because there's a certain portion of the population that has enough energy to sort of escape. And that's the same thing with the sun. It's hot enough that you've got particles that are energetic enough that they can escape the sun and come out. It's pretty impressive, the number of those. That's 10 to the 36 particles per second. That's a rough number. That's a 1 followed by 36 zeros. That seems like a lot. And in fact, that is. It means about 6 billion tons of mostly hydrogen come off every hour. And that seems like a lot, but you got to remember the sun's a very big object, and it would take a long time, even at 6 billion tons per hour, for it to all go away. So there's no concern that we're going to lose our sun very soon. The particles are predominantly electrons or protons because the sun's mostly hydrogen, and that's just an electron and a proton put together. There's some helium ions and some other exotic things, but it's mostly protons. So there's some typical values in case you want. At 1 AU, which is the radius from the sun to the Earth, by the time it gets out there, the speed's kind of going like 240 miles per second. Now that's not miles per hour, that's miles per second. So it's really clipping along still. But it still takes 3 days or so to get from the sun to the Earth, even to that speed. The density is about 4 particles per cubic centimeter. So that's about the size of a golf ball. You'd have a little less than 100 particles in there. So very, very tenuous, very, very thin stuff. And because it's charged particles and there are currents flowing in there, you get magnetic fields associated with it as well. That magnetic field is it's a 4 nanoteslas is a pretty useless number unless you know what the nanotesla is. For reference, the Earth's magnetic field is about 60,000 nanoteslas. So it's a very small field compared to the Earth's field, but it's also a very big cloud that's moving past the Earth all the time. And it's always going past. So the question is, why don't we get aurora? Why don't we get these perturbations happen all the time? And that we can see from here. But because it turns out it's the orientation of that magnetic field that goes along with the solar wind that interacts with our magnetic field that makes all the difference. To show that, here's a little movie that NASA put together several years ago. It's highly stylized, but it sort of shows the idea. And what it is it shows that when the magnetic field in that solar wind is pointing downward, that it interacts with that interacts with our magnetic field, and that transfers energy in a special way. So here we go. So like I said, the solar wind always comes out, but sometimes you get these storms called coronal mass ejections, and this is sort of a artist representation of that. It comes along, and if it runs into our Earth, you can see you actually break apart magnetic fields on the front side, and they can stream back to the back side. Sort of enhances that sort of teardrop shape. And that will actually cause actions at the back of the magnetosphere, the tail we call, that will accelerate the particles down and create the aurora. And that's all great because that's what causes the aurora, and that's what we love to see. But what I want to talk about now is still this sort of transfer. You get this sort of disconnect between the solar wind magnetic field and the Earth's magnetic field here, and that will drag field lines, magnetic field lines, back across this way, and then they sort of compress back here. That's very stylized. Here's a little bit different version of that picture. Again, you can see it breaks off here, and this goes like this. Now, this is important because another fellow back in the 19th century was looking at magnetic fields and currents as well, and what he found is sort of the opposite. He says, if you take a magnetic field and change it, it actually produces an electrical force, or it'll actually produce a voltage in certain cases. Well, this is certainly a case where the magnetic field is changing. You're dragging the magnetic field from the front of the magnetosphere to the back of the magnetosphere. So you're just dragging that magnetic field back. That changes the magnetic field. So we actually end up with a voltage or a force across there. So here's the sun over here, and we're going back that way. Unfortunately, I rotated this image like this. So here's the sun up here. We're looking down on the top of the Earth. Here's noon and here's midnight. Those field lines are dragging across like that, and as they move across there, they're separating charge and producing basically a voltage across here. So this is about 60,000 volts from one side to the other side. And that happens on a regular basis when you've got nice active stuff like this. Now we got to remember to go back. If the solar wind field is to the north, it doesn't do this reconnection, and it just kind of goes by, and this voltage actually goes down. So that's the change in the voltage. That's our battery. That's what creates the energy that's going to drive the currents in the ionosphere. So we've got our battery now, and we understand why sometimes it's there and sometimes it's not. Now let's talk about how we create the wire. So we'll talk a little bit more about what actually causes the aurora, and that's electrons that come from that tail of the magnetosphere. You saw that energy over here. It released that magnetic field. That sort of accelerates those electrons along the field line. And by the time they get to the top of the atmosphere, they're very energetic. They can have 10,000, 20,000 volts of energy in them. When they come down, they start bumping into constituents of our atmosphere, atoms and molecules that are up there. And a lot of times they'll just bump into, say, an oxygen atom and produce, well, they basically excite that atom, and that atom then relaxes back down to its ground state. When it does that, it produces a little bit of light. And that's kind of the red and some of the green, that's mostly the green and sometimes the red emissions that you see. And it goes further down, you actually bump into nitrogen molecules, and you'll see this sort of pink-purple lower border of the aurora. Those are nitrogen emissions. But while it's doing this as well, some of those electrons are very energetic, and so they can actually knock another electron off of those atoms or molecules. When it does that, that atom or molecule now becomes an ion. It becomes electrically charged, and you've got an electron over here that's electrically charged. When that happens, you now produce what's called a plasma, which is a partially ionized gas. And like a regular gas, it still responds to pressure and temperature, but now if you add an electric field or a magnetic field, it has to respond to those as well. And unlike a neutral gas, like we have down here, it can actually carry a current because it's got those free charge particles. If you apply electric field, those particles will move around, and if they move differentially, you actually get currents. And the more charges you have in that, the denser the plasma is, the more current you can actually support. So that's kind of the basis of what we're talking about. So we can show that ionization is caused by the aurora. What I've hidden behind this movie right here, we have what's called the Poker Flight Incoherent Scatter Radar. It's a radar run by NSF and SRI Incorporated. It's what's called an incoherent scatter radar. It's got high power transmission there, and it looks at the reflection off of charged particles in our upper atmosphere, and that tells us not only the density, but it can also tell us the temperature of those particles and also which way they're moving. But we're going to be interested mostly in how many particles there are at any one time. So if you see this, it's a big flat area. It's now what's called a phased array, and instead of the old incoherent scatter radars, which were these big dishes which you had to spin around to actually map out the ionosphere, you can actually do so essentially in instantaneously change direction by just changing the phase of the beams that come out of those antennas. So what I've got here is I've mapped out an all-sky camera mapped it out geographically, and on the top of that I've mapped out some of the beams that this radar is producing. And what I've done is color-coded how dense the plasma is, how many particles, how many charged particles there are per unit volume in each region. And this is a logarithmic scale. That's 10 to the 10, that's 10 to the 11, that's 10 to the 12. So that's 100 times more dense than down here. And what you'll see is as the aurora moves back and forth across where the radar is measuring, you'll see that it goes from sort of this blue to sort of teal color all the way up to the red when you get those really active aurora. So hopefully this works for us. And there's just a short clip, but it gives you a sense of what's going on. So you can see some auroras to the south of the radar right now. It gets excited, you can see, and then all of a sudden, each of those beams goes red, which means the density of the charged particles in that region went up. So it went from something that had very few particles, would probably not carry as much current, to a region that can carry that has quite a few particles, and therefore can carry a lot of current. This is just showing sort of a time history of the same thing. This is altitude, and this is one of the beams in time. And you can see at higher altitudes, there's actually quite a bit of charged particles, but when the aurora comes along, you can see down here, there are periods when you get significant ionization at that altitude. And again, remember, I talked about this happens between the currents we're talking about happen between 100 and 200 kilometers. This is the region we're most interested in. We can talk about maybe why those don't happen there. There we go, it's going to start the movie again. So we have our battery. The solar wind produces this dynamo across the poles that creates a large voltage across the pole. And then we have our wire, which is ionization that's caused by particles coming in and ionizing the upper atmosphere or what we call the ionosphere. And so now we can sort of predict when and where these ionospheric currents will flow. And this has been measured for quite a long. As soon as people put out these magnetometers, even like Carl showed years and years ago, people were seeing these currents flowing all the time. They've come up with a name. They're called an auroral electrojet. Electro just because it's driven by an electric field, and the jets just because it's very large currents at time. These can cause millions of amperes of total current flowing at any one time. And because of those very large currents, the perturbations we see on the ground are a few percent of the Earth's constant field. And if you think in terms of, say, pressure in the atmosphere, that's kind of like having a hurricane go through. So these perturbations are large and very noticeable. And because they're so large, they can produce some real problems. Again, we go back to Faraday. It says a change in magnetic field produces an electrical force. Well, if that change happens to go through, say, a wire loop like that, if you do a large change through there, you're going to get a very large voltage across that, or voltage around that loop, and that will actually drive a very large current. And that can be a problem for long loops of metallic structures, say, for example, a transmission line or a pipeline. So when these large currents happen, when these large magnetic fields are produced and change quickly, they can produce what's called geomagnetically induced currents. And those currents are not what you design your transformers for your transmission line to be. And so if you're running your transmission line at 60 hertz, like most transmissions line go, and you drive sort of a DC current through that same transformer, that can heat it up, and at times it can actually damage the transformer. Then GICs can also drive currents through pipelines that will then be sort of grounded, and that can cause corrosion in the pipeline. And in fact, the Alaska pipeline, they put in sacrificial anodes that would help in reducing the amount of corrosion that's happening. So they took care of that. They thought of that in the past. But there have been problems, as Carl will point out. On March 13, 1989, which I'll have to say was a night that saved my master's thesis, there was a very, very large solar storm that produced quite a bit of auroral activity, but it also produced very, very large GICs. And at that time, Hydro-Quebec, one of their systems took enough current through their transformer that it actually failed. And because of that, it sort of cascaded, and several other transmission or substations failed as well. And for about 9 hours, a good portion of what was called Hydro-Quebec was out. The picture to the right is not the Hydro-Quebec, but at the same time, there was a New Jersey public service that also had some damage to a transformer. That shows that as well. So these are real things. Since 1989, our solar cycles have been smaller. Some of our storms have not been as big, but as we've become more and more centralized in terms of power distribution, we are continue to be worried about that. Another aspect was in the Toronto Stock Exchange, there was a storm in that summer as well. That one thing that also happens is those produce also high energy particles, and that took out some microchips in one of the computer systems, and so the Toronto Stock Exchange went down as well. That doesn't have anything directly with the GICs we're talking about, but it does show that overall space weather is a concern for people. So not surprisingly, a lot of people are studying this, and the Geophysical Institute is included in that. So we have a group here led by Professor Connor at the GI and co-PI'd by Professor Keese at University of New Hampshire, looking at trying to predict when we're going to get these large geomagnetically induced currents, and based on solar wind conditions. So if you watch the solar wind, we've got satellites that measure the solar wind coming in all the time. We can see changes when we see that negative BZ, and we see very strong currents, and we see very strong flows in the solar wind. We can try to predict how that's going to play out in our ionosphere and when it's going to produce very large GICs. And this is some early work by one of our graduate students trying to predict some of those spikes in there based on the time series of the solar wind coming in. So the point here is that can we then have basically signals or warning signs for power companies to be able to maybe adjust their operations in response. Now, part of that, the more information we have about magnetic signatures, the better. So one thing we're doing right now is as part of our education public outreach part of this project, is to include funding to have some students and teachers build their own ground-based magnetometers. So right now we've got one high school student, one undergraduate, and a couple of graduate students. They're building and testing some of the first units now, and the picture on the right is just sort of an early version of that where we're still sort of getting things together. This summer we're planning a summer class for teachers to show them so they can build their own versions of these and learn a bit more about magnetic fields and measurements and the GICs. And then in the next couple of years we hope to work with villages and communities across Alaska to get them involved. And the idea is they will build that and we'll set it up as a ground station, and then instead of having 8 or 10 sites that we run right now for our magnetometer, which are very sensitive, we'd have lower sensitivity magnetometers but have a lot more of them. This is very appealing because the more we have, the better we can sort of pinpoint where these currents are flowing, and we'll be able to predict better when we might have a problem with very strong ground-induced currents. So if you're interested, give me contact me by the email down there, and that'll be at the end of the talk as well. So to summarize, the perturbations we see on the ground are due to currents that flow in our atmospheric region called the ionosphere. Those currents are driven by the solar wind. The solar wind produces the battery, the energy for those, and the ionization that the aurora produces channels in which that current can flow. So now you know why we measure those little squiggly lines in the magnetometers all the time. They're very important for what we do. And now Carl's going to tell you that sometimes you see squiggly lines in other instruments, not just magnetometers. So thank you very much.
In part 3, we're going to look at recording geomagnetic storms and auroras on seismometers. This is the part that brought Don and me together on this topic. And it sort of starts with seismologists Thomas Forberger and Adam Ringler publishing papers in 2007 and 2020. And from that, we sort of made this team to look at the connection between the aurora and seismometers. Seismologists suspected that magnetic fields could generate unwanted noise on seismometers. Some of the key interesting events in the story in the 70s, testing gravimeters in a centrifuge designed to mimic the gravitational forces of the Saturn V rockets for Apollo missions. They found this sort of magnetic susceptibility. And there were also 2 strikes of electric streetcar workers, one in Zurich and one in Stuttgart, that proved that magnetic influence on seismometers. In other words, when the workers went on strike, the noisy signal that they'd been always seeing disappeared, and they could tell that it was of magnetic influence. So if electric streetcars could cause problems for seismometers, what about geomagnetic storms? This is one of the events mentioned in Don's section there, 1989 magnetic storm event in Canada. From the abstract, it said this event has become the archetypal disturbance for examining the geomagnetic hazard to power systems. And this is the event that started getting the attention of seismologists. Some had noticed signals appearing that they suspected were related to the magnetic storm. But the one that really tipped things off was in February 21st, 1994, another coronal mass ejection, as they're called, hit the Earth, and this appeared in the data, and in particular on seismometers in Germany. This shows a publication in 2002 looking at a recording on a seismometer on the top and a magnetometer on the bottom. And this is over, sort of dozen hours or so, and the signals are strongly correlated. There are similar swings in the magnetometer signal and the onset as in the seismometer. So this is where kind of the first published example of this connection. If we look at that same 1994 event recorded here in Fairbanks, COL stands for college, the station near campus, and you see over a 24-hour period or so here, this is the station in Germany, and this is the station in Fairbanks. You can see the onset at 9:01, the Earth gets hit with this coronal mass ejection, and then there are hours of activity that are not exactly correlated, but it's much higher than the typical background range that you would see before this. So this led to the study which we published last year, recording the aurora at seismometers across Alaska, and our team was Adam Ringler, seismologist from U.S. Geological Survey, Don Hampton, space physicist, and me, a seismologist. So this is where we're going to finish looking at the connections we made here. The first one is a map of Alaska, and it's really an inspiring look at data acquisition for geophysics in Alaska. The blue triangles show right now the coverage of seismic stations in Alaska. It's a monumental achievement if you imagine what it takes not only to get to these places, but to have a power system transmitting data such as infrasound, wind speed, weather, seismic ground motion. So we see this expansive coverage of the state thanks to the EarthScope seismic array. We also have dedicated observatories for magnetism, geomagnetism, shown in these orange dots here from the U.S. Geological Survey. And then we also have the areas where we have all sky cameras as the squares and geomagnetic sensors from Geophysical Institute here, providing more dense coverage, but not as dense as the seismic coverage that we have. So the idea here is if we can exploit the seismometers in some way, we would have better coverage to work with. This shows a figure from Adam Ringler's paper that is showing Fairbanks seismometer without magnetic shielding and with magnetic shielding. And you can see that without the magnetic shielding, the blue traces up here look very similar to the magnetometer that's on the same site. So the magnetic shielding removes the effect that generally you don't want to pick up on a seismometer. But if you are going to pick up the magnetic field recording, then we might do something useful with it, such as monitor fields related to aurora displays and dynamics. If seismometers can record space weather events, such as in these three studies, then what are the seismometers recording during auroras? That was the question we asked. And note that there are other non-atmospheric sources of magnetic field variations recorded by magnetometers. It'd be nice to verify that these seismometer recordings are associated with space weather through the visual connection. So a common question we get is, how did you figure out which particular nights to study? And for that, the answer is, went online to the Fairbanks Daily News Miner search and typed aurora photo. And out came this beautiful photo. This is 2019 by Aaron Lejeski, who runs Fairbanks Aurora Tours. And I thought, well, that's a really nice display. Why don't we start there? And so from that photo, we looked into the seismic data, and as it turned out, the photo really kind of catapulted our study toward wider audiences just because of such a beautiful photo. It was on the cover of the published volume with 51 papers in it. It appeared as a little news blurb in Science magazine. So I think the photo brought some people into our research to try to understand what we were looking at. And what we see here is there's the photo at the upper left. At the same time, we have an all-sky image showing a picture of the entire sky taken from Poker Flat. And we can see the magnetometer and a nearby seismometer showing very similar recordings during this 24-hour period. And the onset of this sky kind of bursting into the pinks is shown here, where things tend to increase, this alignment right here. So if we look at this juxtaposition between the sky, we can compare then again with the magnetometer recordings. This came up earlier in Don's talk. But what we're seeing is that the magnetometers at Tulik in the north, Poker in central Alaska, Trapper Creek toward the south, we can look at snapshots in time shown on the top. This is 5:53 UTC, 8:38, 9:24. At different snapshots in time, we can see the sky, and we can compare that with what the recording of the magnetometers look like. And from that, we can identify the sort of events that are occurring, sort of perturbations from the background. Here's 1, 2 is a spike here, a third spike here, a fourth one, and then a fifth one here. We can also see that at other times between these, such as the middle panel here, there's not much activity going on the magnetometers across the state. So just qualitatively speaking, when the sky is quiet or not as bright, the magnetometers are also not as bright. And yet here, we can see during this first peak, there's a lot of activity in the sky. Same within this second peak shown with event number 3. So this first connection is between the sky and the aurora, something that Don focused on. That leads us to the seismic stations. At this particular time in 2017, there was about half the state covered, so it wasn't complete coverage. But we can collapse or sum up all the signals appearing within geomagnetic latitude bands as a way to enhance the signal. There are other effects that get suppressed when we stack these signals. And so what you're seeing here is for magnetic latitude going to the north, we stack the time series of basically the energy at very long periods. And what we can see here as a function of 24 hours, things are kind of going along. There are also earthquakes that get recorded. So it's not just the magnetic field signal we're capturing, but there are earthquakes as we might expect. And then here's these 5 events that we saw on the magnetometer. The first one, here's a spike. Here's the third one. The second one, a spike. The third one, the fourth one. So that at least qualitatively, there are spikes in these examples. And we also see, as you might expect, that as you go north, the signals get stronger. And that's also what we see in the sky. The aurora is stronger toward the north in these regions. And we can see that the signals are enhanced to the north. So this is showing, with the numbers coming from the magnetic and sky events, that we have some qualitative connection with what you might never guess, which is an instrument designed to record the motion of the ground happens to act also as a magnetometer, inadvertently. And the last real most direct connection, just shown in one image here, this is a seismometer recording for a particular night. And we see here that the enhancement of the seismometer recording, if we take what is called the envelope of the energy of this function, it's shown below here in gray. It's just sort of a plot showing where this energy is peaked as a function of time. And we can see that the gray nicely matches with the intensity of the color as captured by the all-sky cameras. Not surprisingly, green is the main color being picked up. But you can see that the correlation when the sky is colorful, the seismometer is also giving us a signal. So in one figure, you see colors in the sky connected with recording from a seismometer. And that's sort of the essence of what we demonstrated. In summary, Space weather and auroras are measured in Alaska using multiple instruments, including cameras and magnetometers. We've shown that seismometers are sensitive to changes in the magnetic field, such as those associated with aurora activities, and in essence, a seismometer acts as a crude magnetometer. So if we look at the right, back to the start, we have all this complexity going on in the night sky, and the idea is with all these stations on the ground, even though some are seismometers and maybe crude magnetometers, we could probably capture more about what's going on in the sky by monitoring the magnetic field on the ground. And so more magnetometers would enable better monitoring and scientific discoveries. Until then, we can exploit the current coverage of seismic stations to examine magnetic fields associated with the aurora. This is a really exciting time for seismology in Alaska and possibly opening up a lot of new avenues for aurora studies as well. Thank you very much for your attention. Good evening.